This exercise follows up from the previous exercise, which follows up from code earlier in this chapter. We are continuing to explore the implementation of linear weighted combinations using different aspects of Python code. Okay, so let's switch to Python and I'll show you what I mean with this exercise. So here I have, again, the scalars and the vectors as lists, objects in a list. This is exactly the same code as in the previous exercise. This is also the same, initializing the output lin combo, linear combination. And now I've just set up this for loop slightly differently. So I'm indexing each of these lists instead of zipping them up together. So first I'll run this just to confirm that we get the same answer as before. Wait, I should print this out. Lin combo. So here we see we get the same answer as before. And yeah, I guess what I want to show now is whether this gives an error or not depends on where you add an additional element here. So we can repeat vector v1, for example. And here we do not get an error. And also v1 as a second thing is not actually doing anything. And why doesn't it do anything? Well, that's because we are defining this for loop to go up to the length of scalars. And I haven't changed the number of elements in scalars. So in fact, this is still just going up to 3 numbers, so 0, 1, and 2. So in fact, this element here just gets completely ignored. But, we can add, let's say, 5 over here, and now we get an error because the list element is out of range. It's trying to find a matching vector to go along with this scalar. So there's, it's a fairly simple, straightforward exercise, but there are a couple of educational points that I wanted to make with this exercise. One is just to give you more experience working with linear weighted combinations in Python. Make sure you really understand this concept. As I mentioned in the previous video, it's fairly straightforward, but it's so foundational. There's so many operations in applied linear algebra that are based on this very simple principle of linear weighted combinations, scalar times vector, and then you add more scalars times vectors. A second point that I wanted to stress with this exercise is that when you're taking a linear weighted combination, of course, it only makes sense to do that when the number of scalars matches the number of vectors. Kind of conceptually analogous to a dot product, where it only makes sense to compute the dot product between two vectors that have exactly the same size, exactly the same dimensionality, the number of elements. And then the third point here is, just to convince you yet again that this way of implementing linear weighted combinations is fine for this chapter, but in practice, you're really not going to want to deal with this complicated stuff that's really error prone. The elegant solution in linear algebra is matrix vector multiplication, and we'll get to that in a few chapters.